Hello everyone. This is another video in the system design interview preparation series from codeKarle. Now this is something that has lately been asked very frequently by a lot of companies. So let's look at how do we build a video conferencing application or a video chatting application, something very similar to Zoom or WebEx or WhatsApp video call or Facebook video call, Google Hangouts. There are a lot of these guys. So let's try to build one of them. Also, near the end, we'll try to look at how could we enhance this platform to build a live streaming system. Something, for example, if you want to stream a live speech of a politician, or if you want to stream a live game or a match, how do you do that to millions of users? Let's look at some of the functional and non-functional requirements that this platform needs to support. So the very first functional requirement is that this platform should support a one-to-one calling feature, wherein one person is making a video call to another person. Okay. The next obvious feature is that it should support a group calling also. So maybe 5 or 10 people could come together on a group video call or an audio call, and they should be able to see each other's screens or picture or anything, right? The next thing is these calls could be audio calls, could be video calls, and people would also be allowed to do a screen share. Now, video and screen share are fundamentally the same thing. It is just a stream of video content whose input source is now different, right? Input source for a video call would be a camera, and input source for a screen recording would be a screen share. But fundamentally, both of them are still implemented in a very same way. We'll also allow our users to record these video calls in case they want to look at it at a later point in time. Now, this screen recording is supported in some of the platforms like Zoom. All the personal use apps like WhatsApp and all don't support that. So we'll not go into too much of detail on this, but we'll still go over it a little bit. Let's look at some of the non-functional requirements now. So the very first thing is that this platform should be super fast. Now, if you have seen my other videos, I generally say that the system should have a low latency. But in this scenario, low latency would not be good enough. So if you do a comparison with YouTube, if let's say a video on YouTube is buffering, that would be okay. People would realize that it is probably buffering because of low network connectivity or whatever. But when you're on a video call, you cannot have a lag, because if you start having a lag in a video call, and that too in a group video call, that would be a really, really bad user experience and nobody would want to come on this platform. So we need to absolutely make sure that the platform is super fast and it almost seems instantaneous conversation. Okay. The next thing is that the system should have a very high availability. It should be fault tolerant in terms of hardware, and also distributed geographically so as to provide low latency and durability. The next thing is that in some scenarios data loss is okay. So the idea of data loss is, let's say if you are watching a video and if a couple of frames of the video are missed, normally you wouldn't even realize that. And that too, when you are on a video call with somebody, if a few frames get missed, it really wouldn't make a difference. So if we have to compare amongst all the three with latency, availability, and absolute data consistency, consistency is what we'll be okay to let go of if we are able to get a better latency and availability. So let's try to look at how can we design the system given all of these constraints. This video basically takes an inspiration from another video that I have made, which is on building a chat application like WhatsApp. There were a lot of concepts that were introduced in that video which we'll be using here, and we'll extend the whole design to now support even video capabilities. So I would recommend to watch that video first before watching this video. Now, assuming you are aware of how do we build a chat application, let's go over some of the conceptual things which we'll be using in this video. And let's try to understand some protocols on which internet is based. Let's look at how does a client application talk to a server, right? So normally when you are building a system design, you will have a couple of services that are sitting on the backend, a couple of clients which are talking to them, right? Now normally these would be implemented as REST APIs or some kind of an APIs which would generally work on HTTP protocol. To make it secure, nowadays we are using HTTPS generally instead of HTTP, right? So that is one way to communicate. Another way could be wherein you need to build something like a WhatsApp, wherein a server might want to send a notification to a user, or a user might want to send a message to the server, and you need a bidirectional communication protocol. For all of those kind of use cases, we use something called as a WebSocket, right? Now, both of these HTTP, HTTPS, WebSocket, all the three of these are basically built on something called as a TCP, which is a transport layer protocol. Now let's try to understand how does TCP work and why are we talking about that in this video particularly. So the way TCP works is, let's say you have a client which wants to talk to a server. So the very first thing as part of TCP that happens is a connection is established between a client and a server. Now the way connection is established is client sends a message to a server saying that I want to connect to you. Are you okay with that or not? If server has resources to connect to that client, server will send back a response to the client saying, yes, I am okay, let's connect. Then client will send a confirmation saying, okay, great, we are connected. And then is when a connection is established between a client and a server. All good till now? Let's talk about how does the data flow happen. So let's just say, so everything in the TCP world is in the form of packets. So there are packets of information that are sent from client to server. Okay. So let's say the client wanted to send a packet which has some information, and let's say it has a ID P1. Okay. Now to send P1 to the service, what client actually does is it says that I am sending a packet P1, which is a packet number one for this kind of a communication that we are having, and sends it to the server. The server then sends an acknowledgement back to the client saying, I have received P1 packet. Okay. Now, till certain point in time, if a client does not receive an acknowledgement, it again sends the same packet P1. Okay. Now, furthermore, the client will send more packets P2, P3, P4. Each of the packet will have this number 1, 2, 3, 4, 5. It will not be 1, 2, 3, 4, 5 kind of a number, but logically speaking, some number through which the server would be able to identify the order in which the packets are supposed to be received. The whole idea of doing all of this is that TCP is basically a lossless protocol. It tries to the best of its ability to make sure that there is no data loss happening between a client and a server. And wherever it figures out that there is a potential data loss, let's say if it did not get an acknowledgement for a particular packet, it tries to replay that. Also on the server side, it tries to arrange all of the packets in the same order in which they were supposed to be based on this number, and then sends it back to the application. So TCP does all of these things for you. There are a couple of other things also that TCP does. One of the things is called congestion control. So if let's say TCP realizes that there is too much congestion on the network, it delays sending certain packets so as to make sure the network is not overwhelmed by a lot of packets. Okay. Now these kind of things are sometimes good, sometimes bad. What we are seeing here is for each one packet of information, there are three data, there are a couple of times the data is being sent, right? Now, in our scenario, that is a very bad thing. Why? Because remember the non-functional requirements, we are okay with some data loss, but we want the communication to be fast. First of all, to establish a communication, there is a three-way handshake. Then each packet comes up with a lot of additional information about the sequencing and all of those things. So generally a TCP header would roughly be 20 bytes. Okay, and that's a lot of information. And we should try to minimize that as much as possible. Okay, so that is, and then congestion control on top of it would sometimes even slow down sending the packets from the client itself. Now that being used for a video chatting application would slow down our experience totally. Why? Because one packet information gets an acknowledgement, maybe gets retried, too much of traffic, probably not worth it. Okay, so let's try to look at some other alternates. So this was TCP for you. Okay, now there is something called UDP. UDP is a transport layer protocol again, equivalent to TCP, runs at the same layer, but functionally totally different. The way UDP works is, let's say you have a client and it wants to send something to the server. It keeps on sending the payload irrespective of whether the server is getting it or not. So let's say it has these P1, P2, P3 packets to send. It sent P1, server got P1. Then it will send P2. Let's say P2 got dropped in between. It would not bother to send P2 again. It sends P3 and let's say server gets P3, right? So the server now just has P1 and P3 and P2 got lost in between in the network due to congestion or packet loss or anything, right? Now if you compare this with this, it has a lot less data transfer happening in between. And if you look at the header size of UDP, that is roughly, I believe, 8 bytes or something, which is significantly lesser than the header size of TCP. So there is a lot less overhead to sending each data packet, right? Now, this kind of a thing is a lossy protocol. There could potentially be data loss, but it will guarantee that it will be faster. One drawback here is the packets could come out of order. So server could get P3 first and then P1. So this kind of a thing exists in UDP. TCP on the other hand makes sure it is ordering all the packets by this number that was sent along. So this problem was not happening in TCP. But in our case, we should be okay with that because a couple of packets here and there, a couple of missing frames, a couple of out of order frames should not be too much of a problem for a video conferencing app. So that's the reason we'll be using UDP here. Now, when we say UDP, we'll not be using UDP for everything. We'll be using TCP for all the communication between a client and a server which does not involve video transfer. For all the API calls, let's say a person wants to initiate a conversation with a user, all of those would still be done on TCP. Just the time when there's actually a video transfer happening, that piece would happen on UDP. Now, let's quickly look at how WhatsApp chatting works and then we'll build on top of it. So let's just say there are two users, U1 and U2, and U1 wants to send a WhatsApp message to user U2. So remember the WhatsApp video, there used to be something called as a WebSocket handler, which was basically keeping persistent connections based on WebSockets with all the active users. Okay, so when U1 wants to send a message to U2, U1 will basically inform the handler saying, I want to send this particular message to this particular user. Go send it. WebSocket handler will involve a lot of other systems in between, and in the end, it will send the message to U2. Right? Now, other systems that were involved are not of significance in the context that we are talking about right now. So let's ignore all of that, assuming this is the flow. And then to and fro communication can happen between U1 and U2. Now, let's just say that U1 wants to initiate a video call with user U2. It can follow the same process. It can basically inform the WebSocket handler saying, I want to make a video call to user U2. First of all, handler will check whether U2 is online or not. If the user is offline, it can handle it in multiple ways. So you can discuss with your interviewer and finalize on that. You can either send an error message to U1 or make a ringing call like what WhatsApp does and kind of do nothing to U2. Whatever you want to do, you can do it. But let's just say that user U2 is online, then handler will send a message to U2 saying that user U1 wants to initiate a call with you. Do you want to accept it or not? If the user accepts it, it again flows the same route and the call is established. If the user rejects it, it follows the same route again and user can see a error message or a different UI saying the user has not picked up the call. Right? So now let's say we have a situation where the call has been accepted. Now normally you can do the video call over this whole communication the way chat was working. That would work fine. But remember in the previous section what we said was we do not want to do a video call over TCP. Remember WebSocket is a protocol that is built on top of TCP. For video calling we want to do it on top of UDP. So we'll probably have to do something different from what this is. But along with that, wouldn't it be nice? Let's just say that this server also supports UDP, for example, for a moment. Let's imagine that. Instead of going all the way, it would be really nice if user U1 can directly talk to U2 in a more peer-to-peer way, right? If that is possible, then that would be a much better solution. Why? Because it will give a much lower latency, and now nobody is dependent on a central server. Plus, that reduces the cost also for the service provider because they don't have to intercept all the calls and like transfer the payload from user 1 to user 2, right? So let's try to see how can we establish a connection between these two parties. Now, UDP fundamentally is a connectionless protocol. So there is no connection as such. Whenever somebody wants to send a UDP message, they essentially say that send this particular message to this particular IP address at this particular port. That's what actually happens. But each time I say that there needs to be a UDP connection kind of a thing, it basically means that U1 understands how to send a message to U2 and U2 understands how to send a message to U1. Okay. Now, what does U1 need to send a message to U2? It essentially needs U2's public IP address and U2 needs U1's public IP address to send the message. Okay. Now, there comes something called as a connector. Connector's job is essentially to identify the public IP address of both these users and inform them. Okay. So, U1 will call connector and connector will tell U1 about U1's public IP address. U2 will call connector and connector will tell U2 about U2's public IP address. and then through WebSocket handler they will interchange the each other's public IP address with each other, and then they can start sending UTP message to each other. Okay. Now, why do we need a public IP address? So each time a machine wants to talk to another machine, they need to have a public IP address to talk to. Now, for all the devices that are on IPv6, this would not be a problem, and that's very straightforward. But as far as I know, statistically, more than 70% of the devices in the world are still on IPv4. So this is still a major problem that we need to solve because majority of our users will be on IPv4. And what happens with IPv4 is most of the devices would be connected to their home Wi-Fi router, for example, through a private IP address. So they wouldn't have a public IP address directly. Then their router would also not have a public IP address. That again would have some private IP address. And at the end of it, there would be an ISP router which would essentially have a public IP address. So we need to basically, whatever ISP's router U2 has, that would become the public IP address of U2, and U1 needs to get to know that. Okay, so let's do it in two parts. First, let's identify how does each of the users identify their own public IP address. Okay, so I have drawn a small diagram here to make it easy for us. This is the same connector component. Okay, let's say connector has a IP address of 1.2.3.4. Okay, and these are the three devices that we have in the system who wants to understand their own public IP address. Okay, let's say this laptop has the IP address of 192.168.1.1, which is a private series IP address. This mobile device again has a 192.168.1.2 IP address, and this could be a smart TV, IP phone, anything which has an IP address of 192.168.1.3. Okay, now let's say if this laptop wants to identify its public IP address, then what exactly happens? So this laptop would then talk to ISP's router. Via a lot of routers, it would be talking to its home router, then a couple of more routers in between. At the end, it will talk to ISP's router. Okay, let's say this laptop establishes this connection with this ISP's router on port P1. Okay, externally, let's say the public IP address of this router is a.b.c.d. Now these routers will have firewalls, they'll have something called as a network address translator and a lot of things. So this NAT essentially, network address translator, converts this public IP address into this private IP address. Let's see how that works. So this device would send a message to this connector component asking for its public IP address. Okay, it will send a request essentially to 1.2.3.4. That request will go here. Okay, this router will forward the request to 1.2.3.4. Okay, now when this connector gets the request, it will get to know that I have got a request from from a.b.c.d from a particular port, let's say P1. If this device was connected to port P1 of this particular router, then connector will get to know that P1 was the port through which I got the request. So in the response, it will send this kind of a message. It will say to the same IP address a.b.c.d of this router on this port PI, let's say it is P1 in this case, okay, it will send the same message saying your public IP address is a.b.c.d colon P1. So this device will get to know that my public IP address is a.b.c.d on port P1. Okay. Now same thing happens when this device connects. It will send a request to router connected on port P2 on the router. NAT, then the request goes forward to connector. Connector sends back a response because now it will know that it got connected to port P2 on this device. It will send that request. NAT will convert that request which was supposed to come for a.b.c.d dot p colon P2 for the port to this particular device. Okay, this particular device is IP address, and this guy will also get to know. Similarly, all three of them will get to know that their public IP address is a.b.c.d with individual port P1, P2, P3, whatever that is, right? So this is how a device gets to know their public IP address. So all good till now. So assuming both the parties have got their own public IP address. So let's say public IP address of U1 is IP1 colon port 1, and public IP address of U2 is IP2 colon port P2. Okay. Now once they've got this information, they will again talk to WebSocket handler saying U2 will say that my public IP address is this, inform it to U1. And U1 will say that my public IP address is this, inform it to U2. Now WebSocket handler will inform both the other parties that these are the public IP addresses. Now you can go talk to each other. There are a couple of other things that also happens here. So one of the very common or important thing is, let's say U1 is on a very high speed internet and it can support HD video. Okay. But U2, for example, is on a 2G connection. It cannot support HD video. It would probably have a low definition video or just audio, right? Now, do you think it makes sense for U1 to start sending high definition video when U2 cannot receive it? Probably not, because the communication now will not happen via this. Communication is supposed to happen through this route, right? If U1 starts sending HD packets, U2 will not be able to process them at the same speed that U1 is sending at. Essentially, the experience would be really bad, right? So both the parties will exchange a couple of attributes about their own connections, their own configurations, and then decide on a particular configuration for the video call. Okay. So both the parties will inform what kind of a network bandwidth they are on. They will also inform the kind of codecs that they support, and they will probably also inform about their resolutions and stuff like that. Based on that, a mutual decision would be taken that we will support, let's say, a low definition. Basically, the minimum of the requirements, whichever device has minimum requirements in each category, those minimum requirements are chosen. So if let's say U2 has lower bandwidth availability, then low bandwidth will be chosen. If let's say U1 is on a mobile phone with lower pixels, lower number of pixels, then the communication will probably happen on lower number of pixels, something of that sort. Okay. Now that handshake again happens through the same route via WebSocket handler. Now once all of that is finalized, then is when the actual video call begins. Now that could be a video call, it could be an audio call, it could be screen share, anything. Now it is just a stream of packets which is being sent to either this IP address or this IP address. Now each device does two things. It sends that payload and it receives the payload, right? So the logic of how to show something on the UI or the application would be taken care by the client itself. So each of the applications running on these devices would take care of how do I render the stream of input that I'm getting and how do I render the stream of input that I'm sending out, right? So all of those things would be taken care of at that level. Now, all of this sounds really nice. Then why don't we do this for all the use cases? Why did we have this in the first place, right? We could have built chat also this way, right? But it is not always so easy. Most of the times what would happen is, first of all, UDP might not be supported, right? Because let's say there are, so at this layer, along with NAT, there would be a firewall also, right? Now, most of the times, or not most of the times, but some of the times, some of the firewalls do not allow UDP traffic. Okay, in that case, the traffic needs to then move to TCP and then eventually either on WebSocket or HTTP of the protocols. Either of the two protocols, the communication will move to, right? So all of those things happen. But there is a slightly more technicality even here. So there is something called as a symmetric NAT. What that is basically when this device wants to connect to this connector, it basically connects via port P1, right? So if there is a symmetric NAT, it will make sure that only this connector can talk back to P2. What we are doing essentially is there is this user device of another user who is also talking to the same port, right? In this scenario, there was one connector which got to know of this port, and then there is U1 which is also talking to the same port. But in case there is a symmetric NAT, then this wouldn't work. This firewall will block this connection of U2 trying to access this port. And if that happens, this whole thing goes for a toss. And then we cannot do any of it. So what is the solution? So the solution now is putting something called as a call server in between. What this call server does is basically a combination of connector plus data transfer. Okay. So this call server then, through a similar process, is able to identify each of their addresses. Okay. It gets to know, it sends them also. Okay. Then this serves as an intermediate layer for these two parties to talk to each other. Okay. So U1, it doesn't send directly to U2 any information. U1 basically sends all the information to call server. Call server then redirects all the information to U2. U2 again sends the information to call server, and call server sends the information to U1, right? So this is how the communication, if it cannot happen in a peer-to-peer model, it would happen through something called as this call server. Now, this is not something that I've invented right now. It is a very standard way of doing video calling. So this whole process, what we talked of, is something called as a WebRTC. This is a protocol on which this kind of a communication works. Now, WebRTC stands for, I think, Web Real-Time Communication. Now, all of the handshaking that this WebSocket handler did, this thing is called as signaling in the world of WebRTC. Okay. This connector component that we had, it is actually called something called as stun server. Okay. And this call server that we used, it is something called as a turn server, TURN. Okay. So this is a very standard protocol on which all of these kind of communications are built. Okay. Like for example, WhatsApp video calling, Facebook Messenger video calling, all of those are built on this kind of a setup. Next, let's look at how does this work out when there are multiple people in a call, or you want to have a group chat kind of a thing. So for group video calling, we'll follow slightly different and a hybrid approach. First of all, we'll classify groups into two categories. So all the groups who have less than or equal to 5 users will be the groups which have small number of users, and all the groups which have more than 5 users will be called as group with large number of users. Okay. Now this 5 number is a bit of a configurable number. We'll come to how do we come to this number later on. Okay. But let's take an hypothetical example when there are these 4 users and they want to do a group video call amongst them. Okay. Now let's say if U1 is actually talking about something, U1's data need to be sent to U2, U3 and U4. Okay. Now let's just imagine if these are connected via a peer-to-peer model, what exactly would happen is U1 would send a particular piece of information to U2, then to U3, then to U4 all separately, right? Now for 3-4 users, this is a fairly fine thing. But let's imagine this for 100 users. U1 has to send the same piece of information now to 100 users, right? If this group is of 100 users, right? That's a problem. Mathematically, if we look at it, let's say if there are n number of users in a group, each user's bandwidth utilization is increased by n minus 1 number of times, right? Why? Because each user has to send data to all the users and has to receive data from all the users, right? And this is a bit of a problem. Not a bit, it's actually too much of a problem if it's a large number of users in that group, right? So basis that, we'll say that if these are small number of users, this is probably okay. But if there are larger number of users, this wouldn't work, and we'll follow the approach via the call server. So all the users, let's again take an example of U1 sending a piece of information. U1 will just send this piece of information to call server. Call server would then send to all the 3 users, right? Now what happens? Each user is just sending once to call server and receiving from call server, right? And this takes care of aggregating all the data, sending to whoever is supposed to get, and all of that. Now this call server gets a lot of load in this case, but at least the user's bandwidth utilization are still in control. And this is a much better option because we can scale up this, we can add more hardware, we can increase the bandwidth that this call server has, because this is something which is in our control. But the user's internet connectivity is not in our control. So this is a much better option to route all the calls through call server in case the group has large number of users. Now coming to how did I come to the number 5? So that was a random number. Ideally, you need to talk to your interviewer about what that number should be, but it will not be a static number. It would be a dynamic number. Dynamic in the sense that it would be decided when the call is being created based on the number of participants that are there and the kind of network that the participants come from. So taking a hypothetical example, if let's say all these users are from the same private network, let's say these users work in the same office and they are sitting at their desks and trying to connect onto a call. Now, if everybody is in the same private network, they'll have a very minimal latency. Then we can possibly support even 20 users connected on the same call, right? But let's say if these users are connected from different countries, different geographies, then possibly even for 3-4 users, doing this would be a big problem, and we would want to have this conversation routed through the call server. So that would depend not only on the geography, on the internet connectivity that each user has, and a lot of other attributes. So you can talk to your interviewer about how do you want to drive that thing. There is one more reason why we would want to route all the calls through call server. So remember, we had a functional requirement that we might want to record the call. Now, if you want to do a recording, and if you go via the peer-to-peer model, then there is no way we can record the entire conversation. Either we do that client-side recording and then do an asynchronous push, but that's not too good a solution. So if a call has to be recorded, then anyway the call has to be routed through the call server. If it is a call that need not be recorded, then based on some conditions, you can do a peer-to-peer conversation or through call server, right? Now, normally when you think of a peer-to-peer communication, it sounds that it might be insecure, but it is not an insecure channel. If let's say U1 and U2 are communicating within each other, hypothetically, let's say it's a one-to-one conversation. Even then, you remember there was a handshake that was happening through the signaling server and all of those. Now, ideally, when the handshake happens, they would also exchange a set of cryptographic keys through which the whole conversation would be encrypted. So U1 would encrypt the piece of payload that it sends out to U2, and U2, when it receives the payload, it can decrypt the payload and then play the video. So anybody listening to that conversation in between would have no clue about what is happening. So this is a fairly secure channel. Now again, this can be extrapolated to a group conversation also, and even the group conversations can be encrypted in the same way. Now let's look at the overall architecture of the whole system. Now, if you look at any video conferencing platform, they always have a chat system along with that, whether it be more of professional products like Zoom and WebEx and all of those, or it be more informal products like WhatsApp video calling or Facebook video calling. All of them do have a chat functionality along with that. So the architecture diagram that we'll see now is basically an extension to the architecture diagram that we looked at in the WhatsApp system design. I just included the components that are in addition to that, which would help us to support the video calling feature, but all the chat related products or the systems would anyway be there in the overall architecture. With that, let's get started. A bit of convention to start with. Everything in green is a user interface. Most likely these will be mobile applications. Things in black are the load balancers plus reverse proxy plus authentication authorization layer. Things in blue are the web services or the UDP services that we have developed, and things in red would be the databases, data stores, or some kind of clusters that we use. So the flow begins at a point when a particular user, let's say U1, wants to initiate a call with the user U2. Now all the users who are live in the system are connected to one of the backend components called as a WebSocket handler, very similar to WhatsApp chat implementation. Okay, this WhatsApp, this WebSocket handler keeps live connection with all the users who are active in the system. And there is something called as a WebSocket manager, which keeps track of which machine of WebSocket handler is talking to which user. So remember, there were not one or two of such machines, there were hundreds or maybe thousands of such machines, right? So that's the reason we need something called as a WebSocket manager who orchestrates that which machine is talking to which user. So in case there's a communication that needs to be established between two users, WebSocket handler can talk to WebSocket manager asking for which is the other WebSocket handler machine that is talking to user U2, something of that sort. Okay. Now this WebSocket handler is built on top of, it basically use Redis as a data store. It would not keep it just in memory. It would also persist in the disk to make it a bit more fault tolerant. Okay. So now let's say user 1 wants to initiate a call with user U2. It makes a call to WebSocket handler, which basically calls something called as a signaling service. Now, signaling service is the one that initiates the conversation between two parties. It will also have some policies which will check for certain conditions. So let's say if you have something like a Facebook and you want to put a restriction saying if you are not friends, then you cannot make a video call between two parties or two users, then all of those things would sit within signaling service. It would also use a component called user service, which is basically a repository of all the users in the system to power such functionalities. Now, if there's something like Zoom, such a thing would not exist because there is a concept of guest user in Zoom. So all of those things you can talk to your interviewer and you can, figure out those nitty-gritties. But that's a very small piece, so it should not be a big trouble. Now, signaling service will basically talk to U2 and basically tell the WebSocket handler of U2 to ask U2 if U2 wants to accept the call or not. If U2 rejects the call or if U2 is offline, then it can be handled in certain ways. But if let's say U2 accepts the call, then signaling server basically informs U1 that U2 has accepted your call. Now we can initiate the conversation. Okay. Then comes something called as a connector. So all of the users will talk to all of these components. I have not drawn the arrows because that will clutter the diagram. But now at this point, what happens is both U1 and U2 talk to this connector component. Remember the connector component in the previous segment, which was also called as a stun server in the WebRTC world. So this component is responsible for telling each of the parties about their publicly accessible IP addresses. Okay. Now through connector, they'll get to know their public IP address, and again through the similar WebSocket handler via signaling server, they would communicate these two things to each other, saying my IP address is this, my IP address is that. Now both of them know each other's IP addresses. Okay. Then they will also do another handshake which talks about what kind of bitrate they can support, what kind of codecs they can support, what kind of bandwidth they are having available. So all of those information would also be shared again via WebSocket handler. Okay. Once that thing is established between both the parties, then they can start with the communication. Okay. Basically, then a regular peer-to-peer connection is established between U1 and U2, and they can start sending packets to each other and continue with the video call. Now, the way video call would actually work is those videos would not be, bigger chunks like 5 seconds each. So I've also made another video on a video streaming platform, something like Netflix. There we were using slightly larger chunks. Okay. But in this scenario, we'll use much smaller chunks, which is of a few milliseconds kind of a thing, or maybe, 1/4 of a second or 1/6 of a second, something of that sort. And those big chunks would be sent across to each other so that the experience is nearly seamless. Okay. And it looks more of a real time thing. Now, let's just say it is not able to establish a peer-to-peer connection for whatever reason. Maybe public IP address is not there. Maybe there's a symmetric NAT. Whatever happens, if that is not something that can be done, then comes something called as a call server, which in the WebRTC world is called as a turn system. Okay. Now, each of them communicate to each other through this turn server. U1 sends a message to turn server, and this server sends it to U2. Similarly, U2 sends a message to this server, and the server sends it to U1. So this basically becomes a point which is orchestrating communication between both the parties. This is how your regular one-on-one connection or a regular one-on-one video call would work out. Now, you remember in the beginning of the call, there was a handshake which talked about what kind of bandwidth requirements we have. Now, bandwidth is something that is not very constant. While a call is happening, there could be a network that gets choked in between, and let's say U2's network got choked, and U2 now wants to support a lower definition video instead of a high definition video. Then in the middle of the call also, it should be able to talk to U1 again via the WebSocket handler, saying now I don't have enough bandwidth. Maybe earlier it was supporting a high definition video, but now it wants to support a low definition video. So if those things could be changed in the middle of the call as well, again via the same route of WebSocket handler and signaling service. Okay. Now, each time there is such a change happening in the video call, that does impact an experience a little bit at least, right? As a system, as a person who's made the system, you definitely want to be aware of all such changes, right? So whenever such a thing happens, signaling service would basically put out an event into Kafka. So once signaling service puts that event into Kafka saying bandwidth was changed, it can be further used for some kind of a processing to figure out how stable the networks are in which geographies, and based on that we can make some business decisions, right? So that is something that we need to capture. Along with that, these devices could send some analytics information along with everything, like maybe how frequently the Wi-Fi is changing, what kind of a battery usage is there while being on a video call, how much data is being consumed while on the video call. All of those, each of the devices would send to WebSocket handler, and WebSocket handler would send to analytics service, which is basically purely a system that is taking inputs for analytics. Analytics service that then puts the events into Kafka, which we'll look at later on how can we process. Now, remember we had a functional requirement saying if we have a system like Zoom, we might want to support a recording feature wherein somebody can also look at the recording of the conversation that happened between two people, right? Or any number of people for that matter. So then comes something called as a logger service. So in case it is a recording based system, the peer-to-peer communication would not happen. All the communication would happen to this call, through this call server. Okay. Now when U1 sends a message to call server to send to U2, call server not only sends it to U2, but it also sends to something called as a logger service. Similarly, when U2 is sending a message to U1 via call service, it will not just send it to U1, but also send it to this logger service. Okay. The logger service then basically aggregates all of those small chunks of data and keeps storing that into a distributed file system. Now you can use anything over here. You can use a network file system, or you could use a system like S3, or you can just dump it into Hadoop. You can use anything over here, but the idea is this logger service would be storing all of the small chunks in a permanent data store that is fault tolerant. Okay. Now it would be here just for a short period of time till the time the call is active. Okay. Now, once the call gets disconnected, the, all of between U1 and U2, it via WebSocket handler, signaling service would get to know that the call has been finished. Okay. Signaling service would then put an event into Kafka saying the call has been finished. If somebody needs to do something, go do that. Then comes something called as a file creator. Again, for a lack of better word, I've called it file creator. The idea of this is whenever a call is terminated, this file creator would listen to that event. It would, each call would have a meeting ID kind of a thing, right? And it would, file creator would get to know that this meeting ID has terminated. Similarly, all the file chunks that were stored in the distributed file system would also be stored against that meeting ID. So this creator would basically read all of that data, which is basically all the chunks of that whole conversation, process them, make a video out of it, and store it in another location. I would want to use the Amazon S3 over here because now we need a fairly distributed store because you don't know how many number of times that video would be seen. So we can use this over here. Similarly, you can use any other standard store as well. Now, once it has created a file, it can send a notification to the users who are involved in the conversation saying your meeting has been recorded. Here is the file. Here is the link. Go access it. So that's how this flow would end. Now, let's look at how does a group conversation happen. So remember, group conversation we were building in two modes. If there are a small number of people, like 3-4 people, we could possibly build a peer-to-peer communication between all of them, right? But now each packet of information would be sent to all the users, right? That is one way. The other way is through call server. In case we have like more number of users, let's say hundreds of users, then each device talking to hundreds of others would be too much of a trouble to manage. So then call server comes in. Now, one-to-one communication is slightly different because you just have two parties. You just need to relay the information sent from one party to the other party. But a group conversation is slightly tricky. Why? Because there you need to do something called as a transcoding. If you have not looked at the video that I've made on Netflix, I would suggest to watch that because that talks in much detail about what this transcoding is. But the main idea of transcoding is let's say there is a source video, okay, and there are multiple users who are trying to access it. Each user might be coming from a different kind of a bandwidth ability, different kind of a codec that it can support, different kind of a file format that it can support. So the idea of transcoding is to convert an original video into multiple such formats in which you can support all the devices having wide variety of bandwidth ranges, wide variety of bit rates and all of that. Okay. Now, what happens in a group video call? Let's say there is a user over here, U3 also. Okay. Now this user U3 is having a very bad internet connection. And user U1 and U2 want to have a high definition call. And let's say there are hundreds of users, let's say, but three, for example. The idea I want to do the conversation through call server. Okay. Now U1 and U2 want to have a high definition call. U3 wants to have a low definition call. Now how do you do it? Okay. So what happens is all the packets, let's just say U1 is talking about something and that needs to be sent to U2 and U3, right? So the message would come back to this call server from U1, okay? call server knows that U2 is having a high definition ability, so it would send the same packet that it got from U1, which was in high definition, directly to U2. It also knows that U3 needs to have a low definition video, right? So then it will call something called as a transporting service. Now this transporting service could physically, from a hardware standpoint, be running on the same machine to minimize the latency, but logically it's a different component. So then call server talks to transporting service, transports the high definition video into a low definition format and sends that to U3, right? On the other side, when U3 is talking about something, U3 anyway would talk in a low definition, right? So transporting can happen just one way. You can convert a high definition video into a low definition video, but you cannot convert a low definition video into high definition video. So the video parts that U3 is sending to call server, it knows that it's a low definition video. I can anyway not convert it into high definition. It would send that as it is to U1 and U2. Right? So all that intelligence is built within this call server about each user and what kind of bandwidths and bit rates and all of those things they support, and it would use a cache based on Redis to keep all of that information. Now again, when you have a group call, each of them could be having a wide variety of network connectivity, and each of their bandwidth requirements might change during the call, right? So let's say U3 started off with a high definition requirement, but in between it wanted to have a low definition requirement, right? Something of that sort could also happen. So again, that communication would happen via signaling service, and call service would get to know that now U3 has moved to a low definition mode. So now I need to start doing the transporting service. Maybe earlier it did not have the requirement to do this transporting. So all of those things would be handled by call service at runtime. So now let's look at the last component, which is basically analytics. So there's something called as this analytics engine, which will power all the analytics. Okay. In the previous sections, we had put in a bunch of events into Kafka. This analytics engine would basically read all of those events and publish some kind of reports. Now, if you want to do a very simple analytics, like just figuring out how many number of calls happen in a day, or something very trivial like how many times people generally get dropped off in a call. So if it's a basic set of analytics, then you can basically put all of that information in a time series database and plot some graphs on top of it, and you should be good. But if you want to do some fancy analytics and some really smart things built on top of it, then you can use a Hadoop cluster to put all of that data, and you can run some Spark jobs to basically do a lot of data crunching and publishing out some smarter reports. So all of that could be done. You can have a conversation with your interviewer on what kind of analytics needs to be done. But since we did not cover it as part of functional requirements, I'll keep it here. You can look at any other video which I have made which talks about how to do analytics at much larger scale. Probably a Google Maps video would be a good example of that. Now, let's look at some intelligence that exists within the client. So let's take an example of U1 doing a video conversation with U2. Okay. So clients, as we know, are intelligent enough to identify what all bandwidths they can support, what all bit rates they want to support, what all codecs that they can support, and communicate that to the other party. Okay. They are also intelligent enough to come up with a consensus on what configuration of the communication they would want to support. Okay. Now let's say U1 and U2 are talking in a peer-to-peer fashion. Now let's just say due to some reason there is an issue in the network and the call is getting dropped off, or let's say the public IP address of one of the users is changing, right? In that scenario, the clients would automatically be able to figure out that this is happening, and they would be intelligent enough to mutually decide that we would now move the call from a peer-to-peer fashion to something via this call server, and this would happen dynamically without users doing something about it. Okay, so that level of intelligence also exists within the client. Now, how would that work? So let's say these two communicate via this WebSocket handler and the signaling server, that we need to now move the connection to the call server, right? It need not happen exactly at the same time. Both of the clients can move the communication at their own pace to the call server. So let's say U1 first gets to know that we have decided that we'll move the communication to call server. So U1 will send all the data to call server, and call server will take care of sending that data to U2. But U2 could still be sending the data to U1 directly. And when U2 decides or gets to know that the communication needs to be moved to via this call server, then U2 could basically follow this new route. So all of that can happen independently, and each of the clients can do that at their own pace. Now the same thing could happen in a group conversation also. So group conversation, if it is happening in a peer-to-peer fashion, the clients or the devices could then decide to move it to a call server at runtime if they are having any issues. Next, let's look at how do we use this system to support a live broadcast of some massive event. Now, let's just say that there is a big sporting event happening somewhere. Let's just say, for example, India versus Pakistan Cricket World Cup final. Possibly millions of people would want to watch it, right? So let's see how can we scale this system to work at that scale where millions of users are trying to watch a live stream. Okay. So everything on this side of this red line is outside the scope of the system, but this is because it's input into our system, so that's why I've put it. Okay, so in any kind of an event, whether it be a political event, sporting event, whatever, there would be multiple cameras and multiple audio devices that would be taking inputs, right? So there could be a bunch of cameras, there could also be a bunch of audio devices, right? I'm assuming there is something called as an input manager. It could be a hardware, it could be a software, which basically aggregates all of that and decides that which camera out of those three or five I want to stream right now, which audio device out of those all many I want to stream right now. Okay. It then basically sends me an audio plus video combination into the system that needs to be streamed. Okay. We'll try to follow a very similar model that we had for a group conversation using a call server. Okay. Now, this input manager basically sends the request to a call server saying this is the stream. Now send it across to whoever wants to watch it. Now, the thing with these kind of massive scale live stream is there are a lot of users on a wide variety of devices. Okay, so in our example, let's say there are some or a lot of users on mobile devices, there are a lot of users on TVs, there are another lot of users on TVs, for example, and then there are a lot of other users on laptops. So these are the devices that we want to support. Okay, coming back to this call server, which got an input stream. What this call server will do is it will basically forward the request to multiple transcoders. Now the thing with transcoders is if it's a good enough hardware and we have one input stream and we want to convert that into another output stream of a different format, it can do that at real time. While the stream is coming in, it can transcode it and send it out. Okay. All we need is multiple transcoders, which are a function of how many formats, output formats do we want. So let's say if in this example we have three kinds of users, we'll possibly have three kind of output formats and therefore three sets of transcoders. Okay, so it will send that to all those transcoders, which will then send the transcoded output to a set of call servers. Now, what this call server gets is essentially the file format that would be sent out to one type of user. So in this case, there are three file formats. So there will be three such call servers and three such transcoders. I've made just two for representation purposes. Okay. Now let's say this call server gets all the data for that is to be sent to mobile devices. Okay. It would then send to multiple call servers. Now this call server is not sending directly to users. Why? Because remember, any sporting event would probably be seen by a lot of people in a lot of geographies. So we need a CDN kind of a thing which we can first distribute in a lot of geographies, and then from those geographies we can distribute out to multiple users. Okay, kind of taking an inspiration from something that Netflix has done, wherein they put a hardware at a ISP then and just send that request to the ISP first, and then from ISP it is sent out to users. So a very similar approach I'm trying to follow here. Okay, so this call server would send to multiple such call servers, and all these servers would be geographically distributed across the globe, and then individual call server will talk to one type of user. Okay, so each call server, so if one call server is dedicated for mobile users, then it will talk to thousands of users, but only mobile users, so that it can just work on one stream of data. If there are multiple streams, then we'll have to have a lot of logic about which stream to send out to which user, which will complicate the process. Okay, so this server gets all the data, for example, for laptop users, so it will send out to all those. This call server, for example, gets the input stream for TV users. It will stream out to all of those users. Similarly, both the or as many number of call servers as we need, they would send out the payload to the users that they work for. Okay. Now this management, there needs to be a system that kind of records that which call server is talking to which user in case there is downtime on this call server, we can bring up another call server that can fulfill those particular users. So we can use something like a WebSocket manager that we have used earlier to orchestrate the communication within these call servers. Okay, but that's a very minute detail, so I'm skipping over that. Now, the idea is we want to keep these call servers as close to the users as possible, because otherwise if there are a lot of routers in between, all those routers will have to carry the same set of information multiple times. So as if this call server is close to the user, that latency would be minimized, because this is just a couple of hops in between the call servers, but from call server to users there could be a lot of hops. So we want to minimize the number of hops over here, because this is where the data is getting replicated multiple times. If there are more number of hops on this side, data is being sent only once, so that is still okay if you have a larger path over here. So we'll try to push these servers as close to the user as possible. So yeah, I think this should be it for a video conferencing system. Thanks for watching this video. If you have any suggestions on what videos we should make next or how we could improve this one, do let us know by commenting here. And don't forget to subscribe to this channel, like the videos, and share the videos with your friends while we keep working to get more such content to you. Happy learning!